So this log, remember, is the ratio of organisms, right? 3 log removal of the initial concentration of microorganisms, which is what we're using as our removal parameters. And it could be total fecal coliform, like we did in that coliform experiment. So 3 log removal would be 99.9%. Okay? So the initial to the final, you've lost 99.9%. So that log equals a CT value. Okay? So this, for this case, for the required, what you have to meet in a standard is your required CT. And that's just concentration times whatever time you're using for that react. And so a required CT is the concentration in milligrams per liter of your disinfectant, in this case it's chlorine, times the time that those organisms were inactivated in some experiment, some toxicological experiment. And that gives you a CT value. Concentration times the time it took to inactivate those organisms. And that would be your CT required. And that is what you have in your tables. And this is from the FE. So if you take a look at this, it's the required CT. So CT is just a measurement, right? Does that make sense to everybody? Of the concentration of disinfectant times the time for that reaction to occur to get some removal of those pathogenic organisms. And for Giardia, they have to be 3 log removal. Has to be 99.9%. You've lost. Okay? And so this table tells you the body of the table are the CT values, but they're broken out by temperature and pH. And then on the left side is the concentration. Okay? This part here, milligrams per liter. So you don't have time on here. For this part, time was just the time it took to get that removal, the 3 log removal or the 4 log removal in the study on those organisms. So this is CT. This is required CT. And well, I'll explain this here. The other CT is the CT that you have in your system. So you have a concentration. So the dose of chlorine times the time, which is the detention time. And in this case, we're just talking about pipe flow. So it'd be the average velocity, right? The average detention time associated with laminar flow through a pipe. That's the time. And so those combined gives you your CT actual in your system. So that represents the CT of your system. So what you're trying to do is compare what's required by regulation to what you actually have. And one way to do that is make it a ratio. And if your actual CT in your system is greater than the required CT from this table, from the rules, you're okay. Right? Does that intuitively make sense? If this was less, if it was less than 1, you'd have to either up the concentration or up your detention time, because this reaction is a function of concentration and time, because it's not as effective as it needs to be to get a certain log removal, right? So a certain ratio of initial organisms to the final organism.
Is that greater than one that's at 1%? That's out of that 100%.
Well,
that's why it has to be greater.
Well, this is just a ratio that says what I actually have is larger than what I need. That's just a way to represent it. Just greater than 1. Yeah. I mean, that's all the purpose of this. You could just say my actual has to be greater than my required, right? But if you put it in a ratio, then you can do some calculations to kind of verify it, right? Okay. Does that kind of make sense? So using the actual is pretty straightforward. and I think in this problem, it's just it just gives you a length of pipe, right? So you calculated detention time. And your concentration is gonna be whatever you read with the meter. But to use these tables, for Giardia, this top table, this is Giardia, and then this bottom table is for viruses. For Giardia, you need 3 log removal. And so the problem tells you that at 20 degrees Celsius, a pH of 8, these are all given. And then I think it says it gives you a concentration. So if you look on your lab handout, if it's still the different, it used to be at the top, the problem.
Questions?
Yeah, that last one.
Yeah, the actual CT problem is on page 2.
Okay.
That's the last problem. That's the last problem.
Handout,
Yeah, on mine this was the old one from last
Yeah,
time. It was
I
that
just
one
moved
time.
it around.
Okay. Yeah, so it says, how does that compare? So, you know,
Here, you want mine?
the reading in the chair. Yeah, sure. So I can
That's
get
the last
confused.
problem.
Okay. Yeah, so, okay, it's a little bit different. So yeah, so they ask you for the CT value and the pipe is 25 minutes, right? So you've got a detention time. And they ask you what's the ratio. And then it says, how does it compare to the requirement? It gives you, in this problem, it says,
Yeah, what this problem is, it gives you everything that Dr. Thomas is talking about.
Okay,
It
this
gives
one
you
had-
the 0.5 log numbers, so you don't have to do any conversion. Because of the fact that we have such little chlorine coming out of the faucet, which we're gonna use for testing, we're gonna use the 0.5 log, which is 68, I think, percent reduction, I believe. Yeah, 68% reduction. So we're gonna use that 12.3 milligrams per liter concentration number if you have this. And we'll talk about this after we do the lab and you get your numbers up there on the board. We're gonna walk through how you're gonna calculate these 3 or 5 data analysis problems. But yes, we're gonna use the 0.5 log, all right?
Right.
The 12.3 milligrams per liter, a pH of 8 to 20 degrees. And then we're gonna compare that, that'll be your actual, excuse me, that'll be your required. The actual will be the number you get in your testing that you're gonna have on the board based on 25 minutes. So you're gonna use your concentration, multiply it by the same amount of time that they give you in this problem, then use that as your actual, divided by the required that's given, and then you have your ratio.
right, I was just trying to figure out where they got this part here, less than 0.4 milligrams per liter. Was that measured?
That one's on the table.
Right, that's where I was going, to. I can't remember.
Your guys, like, did they have to give all 3 of them?
Is this,
On which the CT table?
well, let me show you how to use the table,
Yeah.
and then while you guys are working on it, I can figure out how we get this. I can't remember if it's, what we measure or something, but, so like Chicanto was saying, 20 degrees C, pH of 8, you assume those were given to you, and then your concentration is below 0.4 milligrams per liter. So you look on the table, right, and you find 20 degrees C, which is the bottom row, the middle column, right? That's your degrees. Your pH, go over to the pH of 8, okay? And your concentration, which I don't write off the top of my head remember how we got it, but it's related somehow. I don't know if it's given or if that's what you measured, but the concentration is less than 0.4 milligrams per liter. So you have everything you need, right? And you're using the 3 log removal for Giardia. So what you read is 74. Does everybody see that?
So it is the CT.
And that, right, that is your CT. It's not C, it's not T, it's CT. This is C, okay? All right, based on, so you don't need time here, okay? You can solve for time. So you've got, you need 3 log removal because you're talking about Giardia. You're given these parameters. Your concentration is less than 0.4. If you had a different concentration of chlorine, you could have a concentration of 1, right? And that same conditions, pH of 8, temperature of 20 degrees, would give you a CT of 81. Okay? Does that make sense? All right. So, but in this case, we got 74. Then, and again, the problem, I can't remember. The problem asks you, well, what if you need 0.5 log removal? And remember, we can get credit for filtration, depending on the filtration type. So if you got a conventional system with coagulation, flocculation, filtration, you can get 2.5 credits, and that's on that table I showed in class, 2.5 credits for Giardia removal. So you only need, your removal only has to be 0.5. You only need 0.5 log removal, right? So I think 90% is 1 log, so I don't know, maybe 45%, okay, of what's left, because you took most of it out with the coagulation, flocculation, and then filtering. Right? You filtered most of those cysts you're trying to remove. So how do you, well, the question is, well, how do you get the CT associated with that? You're going to use this, you got the same conditions, you still 20 degrees C, pH of 8, your concentration's still the same, but you don't have it on your table. If you had a table with 0.5 log removal, you'd be good, but you don't. But what you can use is a ratio. So the ratio from 3 to 0.5 is 3, you divide by 6. So, because everything else is the same, all you do is divide your CT that you got for 3 log removal by 6, and now you've got a CT for 0.5 log removal. Okay? Does that make sense?